Good morning, class. Let's get started. All along the course of this course, we've been talking about stationary charges. That's when you have a stationary charge, all around it, you will have electric field. The electric field strength reduces as you move away from that charge by a square of the distance with which you move away. The strength of that charge, we said, depends of that field, rather, depends on the magnitude of the charge. And a charged particle, and when it's placed in an electric field, it experiences an electric force. It experiences a force that we can call an electric force, or if you like, you can call it a Coulombic force. This force acts in a straight line in the direction, in the line that connects the charged particle with the electric field. But when a charged particle is placed in a magnetic field, nothing happens. But when that charged particle begins to move, the charged particle will experience a magnetic force. So, a charged particle, when it is stationary, when it's at a position, it can be said to possess electric field around it. But that charged particle, when it's set into motion, in addition to that electric field, it will also have magnetic field. And the presence of magnetic field, because it's in motion, that is why when it enters another magnetic field, or when it's in the presence of another external magnetic field, then we should expect magnetic force. Magnetic force, unlike electric force, does not act in a straight line. The direction of the magnetic field vector is perpendicular to the direction of magnetic force. And when we talk about a charged particle possessing magnetic field when it's in motion, the strength of that field depends on the charge, the magnitude of the charge, and also the velocity with which that charge is moving. So when the charge is moving quickly, we would expect a higher magnetic field compared to when it's moving slowly. So minus trying to understand or grasp the fundamentals that you may have missed out in your secondary school. Somehow, but it's not so much is really new here. So let's look at these bullets one after the other. If there is anyone we disagree with, let us control it now and discard it right away. Stationary electric charges possess electric field. True or false? Anybody objecting to that fact? If there is anybody that objects to that, we just have to start all over from chapter 1. We just have to go back because injustice to one is injustice to all. The electric charges can exist in monopole. It's possible for you to have a certain charge and you say this is positive charge. or negative charge. But it is impossible for you to have a magnet and say this magnet is a North Pole. Magnets do not exist as monopoles. They exist together. So I'm sure you must have seen the magnets one way or the other. And seeing the magnet must have observed if you have put two bar magnets together, you must have observed that there are times they attract and there are times they repel, right? So if you have a magnet, it consists of two poles, opposite poles, named North Pole and South Pole. So let's put that on one side. Let's move forward. Electric force can act on a stationary charge. True or false? Electric force acts in the direction of the electric field. True or false? Silence means consent. The electric force acts on a charge Q in electric field E is defined as the product of Q and E. True or false? So electric charges in motion, so this also possess electric field. So they also possess magnetic field. When electric charges are in motion, they possess magnetic field in addition to the electric field. And the direction of the magnetic field is perpendicular to the direction of motion of the electric charge. So when the electric charge is coming from the back of the glass, it's coming straight, its magnetic field is not in this direction. It's perpendicular. Either this way or that way. It must just be perpendicular to the line of motion. Magnetic substances or magnets also possess magnetic fields. So when you place your magnets on the table, you can imagine what you've done in the past to electric charges. You can imagine them having lines of force, magnetic lines of force, just like we have electric lines of force. These lines of force, we'll be looking at an image very shortly. These lines also are closer to the magnets than when you observe them parallel. So that shows that this magnetic field strength that is experienced is small when you are closer to the magnet. So magnetic force may act on a moving charge, but cannot act on a stationary charge. I've said before, when you place a stationary charge in a magnetic field, nothing is experienced. When the charge begins to move, the charge begins to manifest its magnetic power. It brings out a magnetic field. And when it brings out magnetic field, that is now the excuse for it to interact with any other magnetic field. And if you look at the magnetic force here, there is hope because it's for the fact that it is moving in a magnetic field does not mean it will experience magnetic force, because force is a vector quantity. It doesn't joke with direction. So when the electric charge is moving, the magnetic field is found to have a direction that's perpendicular to the direction of motion. That's direction of magnetic field is important in determining if it will interact with the external magnetic field where it is moving. So if it's such that the magnetic field lines of the generated by the moving electric charge does not is perpendicular, let me that way, to the magnetic force by the external magnetic field, then there will be no need for attraction or repulsion or interaction. So this is bar magnets, and so this is bar magnets, the North Pole, the South Pole. So the North Pole, if we think about it like electric charge, the North Pole is treated like positive, while the South Pole is treated like negative. So the lines of force radiate out of the North Pole and terminate in the South Pole, just like positive to negative when we discuss electric charges. So the small arrows we have here can be likened to be compass, a small compass. When you place, I'm sure we know what a compass is. It's used in navigation, and it gives direction based on the Earth's magnetic field. So when such a tiny compass is placed beside a bar magnet, the magnetic force to be experiencing from that bar magnet will make that of the Earth to be negligible. So when you place a small compass of this nature here, I begin to plot the direction, the points of the arrow. You know, it should give you an arrow on that to show that this is the north. So when you begin to make a point at the base, something like this, you put a point here, another point here, and you bring out your compass again, such that the tail of the tail is now touching the previous edge. So it will form this, it will show that this is the direction of force that is experienced. So let's move forward. So magnetic force on a charge moving in a magnetic field. So the magnitude of the force, let's describe it as, so let's define it as F suspect B. And this magnetic force depends on the charge of that electric charge or of that charge body, and also depend on its velocity, like I've said earlier. So when a charged particle moves parallel to the magnetic field vector B, then FB on the particle is 0. So what this is telling us that we have, assuming we have a magnetic field set up here, let's say we have this Austrian magnet where you have the North Pole here and the South Pole beneath it, in which magnetic field is pointing from the North Pole downwards to the South Pole. And now a charge is passing through that field. When the charge is passing through that field, it will not experience any force if the direction with which it is moving is parallel to the magnetic field vector. So for you to experience the maximum magnetic force, the charged particle should move in a direction that is perpendicular to the magnetic field vector B. In this case, vector B is like an external magnetic field that is applied. So the magnetic force exerted on a positive charge. So what this one is is in the direction that's opposite to the direction of magnetic force exerted to a negative charge moving in the same direction. So when we say that a charged particle is moving through a magnetic field and it experiences magnetic force, that force must have a direction before it is even qualified to be a force. The force is a vector quantity. The charged particle is moving through the magnetic field, it begins to experience a magnetic force. That force has a direction. If another charged particle that is having opposite charge, let's assume the first particle is positive charge and the second one is negative, traveling through the same magnetic field in the same direction with the same velocity. The directions of the magnetic force that they will experience will be in opposite direction, all because the nature of their charge is opposite. So the nature of the charge also depends or determines the direction of the magnetic force. So if a charged body is passing through a magnetic field and it comes to the left because it experienced the magnetic force, it would have gone to the right if it had an opposite charge. So, but the magnitude of the force will still be the same. It's just the direction that would change. So the magnitude of the magnetic force exerted on a moving particle is proportional to the sign of the angle that the particle velocity vector makes with the direction of the external magnetic field. So when it says proportional to the sign, so with the angle between the direction of motion of the charged particle and the magnetic field vector, if the angle is u, or let's say if the angle is theta, you get the maximum theta when at what angle? At 90 degrees. That is when sine is maximum. Sine of angles is maximum at 90 degrees. And at 0 degrees, that is when it is minimum. That is when it is 0. And that buttresses what we said earlier, that when they are perpendicular, when the direction of motion is perpendicular to the direction of magnetic field, we should expect maximum force, maximum interaction. But when it is moving in the same direction, that means the magnetic force may not act on the moving charge. When we say magnetic force may act, it means it may not act as well. So when the direction is parallel, angle theta equal to 0, everything will crumble down to 0. So let's look at some equations. Here we have the magnetic force vector. The magnetic force vector F suffix B is equal to QV. V here is the velocity cross magnetic field strength. So the cross here is not the normal multiplication for those of us in agric and biology. This is cross product. It's not the normal multiplication. When we say QB cross B, is not the same as B cross QV. It will be minus because this is what is a vector multiplication. So when you are multiplying vectors, the direction matters. When I say A cross B, it is equal to minus B cross A. So what that means is that if you use A to cross B, if you use vector A to multiply vector B in a vector multiplication, the value you will get, which you may call C, would be minus C if you had said B cross A. So you should be careful with this for those of us that are not biology. Or those who in biology are free to take it earlier. So what we have in these diagrams is showing that the magnetic field vector, you can see, is F subscript B, is perpendicular to the velocity vector V. If you see the angle perpendicular to velocity vector V. And it is also perpendicular to the magnetic field vector B. If you look at the green line there, here, is perpendicular to the blue line. The red line, which points to the velocity, is also perpendicular to the blue line, which is the magnetic field, magnetic force vector. So when you do a cross multiplication, the answer we get is always perpendicular to each of the items we have multiplied together. So when you think about your graph sheet, you have x-axis and y-axis, right? If you want to advance a bit further and say that your graph sheet is 2D, let us go to 3D. Then you should be able to imagine a third axis that is perpendicular to your x and your y-axis. That your third axis may point out of your paper or penetrate down into your paper. That third axis is, you can call it your z-axis. And that z-axis can be said to be equal to x cross y, because the z-axis is perpendicular to the x, also perpendicular to the y. So along the line, I don't know much about your maths curriculum, but as far as you are concerned, this Q, V, and B are what concerns us at the moment. And a way to also simplify them, I think there should be an expression that says QV. We can say that the magnitude QV and the magnitude V sine theta. Sine theta. And theta here is the angle between the velocity vector and the magnetic field vector. So looking at this, it tells us that you see, let me come back to this diagram. This particular diagram here is telling us different things. It's telling us the original direction and magnitude of V, the original direction and magnitude of B, and now the original direction and magnitude of FB. FB is perpendicular to V and B, no problem, no arguments. But you see the length of this line would have been longer if the angle theta, that is the angle between B and V, if it were to be 90 degrees. The length of this force would have been maximum. And if V has the same direction as B, that is, if the angle between V and B is 0, that is, if the red line lies on the green line, then we would not see any blue line there, because sine 0 would mean 0, and no magnetic force will be experienced when the direction of the velocity vector and that of the magnetic field vector are the same. So for you to have a force, magnetic force, there should be an angle between them. This is one of the things you will not find when you are saying you are doing work is equal to force times distance. You just multiply, you don't care about the direction because work is a scalar quantity. But in this case, we are concerned about the direction. You cannot just say that an electrically charged object moves through a magnetic field and experiences a force. We should be interested in the direction or the angle between the path of motion and the magnetic field. So let's move forward. Do we have anybody that wants to interrupt? So let's move forward. Let me see, check the time. Oh my. The electric field force along the direction of, I think everything there must have said it one way or the other, but let me just read through. The electric force vector is along the direction of the electric field, while the magnetic force vector is perpendicular to the magnetic field. The electric force acts on a charged particle, regardless of whether the particle is moving, whereas the magnetic force acts only when the particle motion has perpendicular components to the magnetic force. The electric force does not work in displacing a charged particle. Sorry, it's like I'm saying double. The electric force does work. I actually saw not there, but my brain now said, is that not wrong? The electric force does work in displacing a charged particle, whereas the magnetic force associated with a steady magnetic field does not work when a particle is displaced, because the force is perpendicular to the displacement. So let me take that again. The electric force does work by displacing a charged particle, but the magnetic force associated with the steady magnetic field does not work when the particle is displaced, because the force is perpendicular to displacement. When we define work again, what is work? How do you define work? You say force times distance. The force times distance there, well, if you like the force times displacement, the force there is a vector, displacement there is a vector, but they multiply together to give you a scalar. What happens there is a scalar multiplication, and it's usually represented with a dot. So when you see a dot, many times in matrices, you mean a scalar multiplication. So this definition is not complete. When we are defining work, we say the force times the distance or the displacement. Also, we mention something else in the direction, right, of the force, right? And so that means that for you to have maximum work done, the force and the displacement must have the same direction. For you to have maximum work done, the force and the displacement must have the same direction. If I begin to push this wall, I don't want to push because I don't want to break it. If I begin to push it, the work that I will do depends on the angle. If I begin to push it at other angles, the work I'll be doing will be reduced. And if I now begin to push at angle 90, it's very obvious that the work I'll be doing will be 0. So the maximum work is when the angle is 0, and the opposite is now the case when we are doing vector multiplication. In vector multiplication, you get the maximum when the angles are perpendicular, when they are 90 degrees. But in scalar multiplication, we get the maximum when the angle is 0. So where we are using sine theta for cross multiplication here, we'll be using cos theta if we were to be discussing scalar multiplication. So I think we can move forward. So let's look at these expressions and let's look at these beautiful diagrams that looks like puff in what's called rolling around with some velocities v, having centripetal and centrifugal forces. So let's start from this expression that says, ordinary puff, you're already sneezing. FB is equal to MA. Okay. All right. Yes. Okay. Sorry, I didn't get it. No, I tried to reduce this to rewrite this expression. Yes. Okay. Let's get there and see where it went. The expressions we have here are for this diagram. That's why they are side by side. So as time goes on, we'll see where they went. Okay. So, sorry, this one in 1-2 minutes will be there. So FB is a magnetic force, and we know force from Newton's law of motion, product of mass and acceleration. So what is acceleration? Acceleration, in this case, we are talking about a particular body. So, okay, now let me try to describe this diagram. You see, we have magnetic field directed into the screen. Those X is showing like the rear view of an arrow. So the direction is like those arrows of magnetic field are entering the screen. So because they are entering the screen, the direction of magnetic field in this scenario is perpendicular to the screen. So the direction of magnetic field is perpendicular to the screen. Now, what we now have here is charged particles moving on the screen right now. So, and they are currently moving in a field which is directed perpendicular to the direction of their motion. So that is established, right? So we can say from here that V, the direction V here, is perpendicular to you looking at pointing into the screen. So for that reason, that's 90 degrees. The angle between, if you insert an arrow pointing into this place, it will form a 90 degrees with the red velocity line. So because it's a 90 degrees, its maximum, sine 90 is 1. That is why we don't have sine theta here any longer. So now we are just trying to look at the motion of charged particle in a uniform magnetic field. And we know acceleration to be v squared over r, where v is a linear velocity, r is the radius, a is also linear acceleration, right? Okay. So now we can replace a with v square over r, and will be, since a is v square over r, then this expression of magnetic force will become mv square over r. And fb, since it's 90 degrees, is qvb. So these are the magnitudes: q, magnitude q, magnitude of the charge, magnitude of the velocity, and the magnitude of the magnetic field strength. So easily we can bring out this expression and this, and then we have a new equation. It seems something is going down. So from this new, oh my. So from this new equation, we can make R subject of the formula, and that will give us mv over qb. So making R subject of the formula, we can come to say that we have, so from this expression, mv over qb equal to R, we can determine many things. So let's move forward. Over V. So V over R, you must have seen V over R to be equal to omega, which is angular velocity. Must have seen angular velocity in the last semester. And if we, from this expression, when we try to simplify and get V over R, it will equal to QB over M. And since V over R is equal to omega, then omega is QB over M. And that means that the angular velocity, which very soon we'll be calling cyclotron frequency. Oh boy. Come back here. Now some people are happy. Okay, so let's deal with this angular velocity, which is omega. Omega, when you think about omega, it tells us the time it takes for you to move round the loop, how fast you move round a cycle, right? So when you move round a certain circle, the circumference of that circle can be described as the distance you have covered, which is 2 pi r, right? So it's easy for us to say that the distance you have covered when you move around the circle, come back here, boy. The distance you covered moving around is 2 pi r. And if the velocity with which you moved around it is v, then easily we can say that this can be defined as angular velocity, because sorry, not angular velocity. Sorry, I'm not designed to shout. So this is like time now. So the time to move round is equal to distance over speed, right? So the distance around the circle is the circumference of the circle, which is 2 pi r divided by v. So that is time, and the time it takes for you to move around a circle or a cycle, can be described as period. So the period, the time takes to complete a cycle, to move around a circle of radius r. So we can now have a period. So that is the origin of this expression. And knowing that r over v has something to do with omega, r over v has something to do with omega, then we can easily come here and say that we are replacing the r over v in this circled expression with omega. And that means that the period is equal to 2 pi over omega. And knowing that omega has been defined as qb over m, then easily we can replace the omega here with qb over m. So the angular speed of the particle omega is often referred to as the cyclotron frequency, omega. So you get the slide, you read. So this is an example. It says a proton is moving in a circular orbit of radius 14 centimeters. If I were you, I would say radius 14 centimeter equal to 0.14 meter. Through a uniform magnetic field, V equal to 0.35 Tesla. Perpendicular to the velocity of the proton. Now, we know that the angle between the velocity and the magnetic field is 90 degrees. So we do, and sin 90 is 1. So it's easy for us to say that F is equal to BQV, like that. So now, find the speed. Then let's go back to your cheats. Find the speed. We know R, we know B. Now we need what? We need V, velocity. So we know R, we know B, it's a proton, we know its mass, right? And it's also a proton, we know its charge. So we know the charge, we know the mass, then everything using this expression of mv over qb equal to r. Then that means we know everything except v. So the force on a charged particle in the presence of magnetic field, we've seen this before. So, but when a charged particle is moving in presence of an electric field and the magnetic field, when a charged particle is moving in the presence of both electric at the magnetic field, it will experience electric force because it's an electric charge and it's in the presence of electric field. It will also experience magnetic force because it's a charge in motion in the presence of a magnetic field. So since they are both forces, we add them together as vectors. That is why we have QE, which we already know. QE here is FE, electric force, is a product of the charge and the electric field strength. So when we add the force, the electric force vector, so this is a vector, not just F, is a, come on, that's too big. So when we add the electric force vector to the magnetic force vector, then we have a total force, which is nicknamed as Lorentz force. So that's Lorentz force. So when we say Lorentz force, what should come to your mind is that the total force as a result of electric and magnetic forces. So the property of a charge, which includes possessing a magnetic field when in motion, can be used in some applications, one of which is the velocity selector. The velocity selector works in a principle such that we have, so let's look at the diagram on the right. So we have a source of charges, electric charges, charged particles. Electrically charged particles are moving through the slits into this region. And what is that region? That region is a combination of electric and magnetic field. The electric field vectors is pointing into the screen. You can see the X signs. So the electric field vector, imagine the electric field lines pointing into the screen. So it's angle 90 to the direction of the velocity. Now, there is also electric field. There is also electric field present in that region. And the direction of the electric field is pointing from the left to the right, from the positive plate to the negative. So the electric field lines are pointing from the left to the right, while the magnetic field lines are pointing into the screen, while the charged particles are moving with a velocity which is obviously perpendicular, mutually perpendicular to the magnetic field and the electric field. So what happens here? We have to go back and look at this, our equation. What happens is that the charged particles, they experience electric force. They also experience magnetic force. The magnetic force they experience is defined as FB equal to QVB. The magnetic force they experience depends on the charge that is passing through and also the velocity of the motion of these charges. So based on the direction of motion, the direction of the magnetic field, we expect the magnetic field vector to point in a direction that is perpendicular to both the velocity and the magnetic field. So you can see that FB on the screen is pointing to the left. the direction is to the left. That direction to the left is perpendicular to the velocity which is moving upwards. And it's also perpendicular to the magnetic field, which is pointing inward into the screen. So the magnetic force should be mutually perpendicular to the direction of the velocity and also the direction of the magnetic field. So because it's a whatever charge it has is pointing to the left, if it were to be carrying the other charge, it would have pointed to the right. So now in this scenario, it's pointing to the left, and it's also experiencing a particular force, another force, electric force, pointing to the right. So if you look at the right-hand corner, you see FP also pointing to the right. So FB is pointing to the left, magnetic force is pointing to the left, electric force is pointing to the right. In this case, when FB is equal to FE, then the resultant will be 0. They will both cancel out. But for charges who have their FB to be less than FE, they will drift to the right. They will crash into the negative plate. For charges who have their FB greater than FE, they will move to the left and crash into the positive plate. So what determines FB, one of the major properties that determines FB here is the velocity. So charges are leaving the source at the base of the plane. They are traveling through that region. It is only those that have the desired velocity to give us FB that will be equal to FE that will travel safely out of that region. So out of that region, we'll be able to say that all the charges coming out of this region have a certain velocity. That is why it is velocity selector. It is only charges that have a certain velocity V, which when multiplied with the charge Q, cross multiplied with the magnetic field B, will give you such a magnetic force FB, which will be equal in magnitude to the electric force FE, such that both forces will cancel out, and the charge particle will move up straight, undeflected. So if you are going into the canteen, rice is pulling you to the right, fufu is pulling you to the left, you are still trying to make your decision. There is a force that is greater that will win. If they both have the same force, you will move directly straight. And you'll stay there undecided until either they run out of rice or fufu, and one will pull you over. So, for those that are fasting, let us leave the kitchen before they start yawning. Okay. I think we should stop here, because you are draining out my organic battery. So we meet on Thursday. Bye-bye.